is exactly underneath, something like that. I make that black in color. Move it. So that's right there. Okay. Now, let's start with the obvious points. Derivative tells you the slope, right? So do you see the slope is 0 right there and right there? So when x is equal to 0, this is your derivative, where this is your f. You get it? So it'll go through 0, 0. You know what I'm saying? And also right underneath at 2, it'll go through that point. You with me? Now let's guesstimate the slope right. That is not straight. Right about there. Is that negative 2-ish or negative 3-ish? To me, it looks like negative 3-ish because this is the slope and this is negative 1. That's not half. That's like probably 30. This is more of an art than a science. So we cannot measure the slope exactly. But our guesstimate right here is 1, 2, 3. Somewhere here, right? You with me? Okay. Now let's try to guesstimate it here versus and here. Those two look about the same, right? What does it look like? 4, 5? I mean, it's way more than 3 now, isn't it? So we cannot exactly measure it, so let's say it's way more. That looks about like way more. And then the other side, that looks like way more, right? Somewhere there. Now we connect them with smooth, and then the slope here changes gradually. Where's my mouse? Right here. Gradual change. There's no sudden change, right? So there's no pointiness anywhere. So this thing changes gradually, and watching the vertex, making sure this is not flat because it triggers certain unnecessary and painful memory in your teacher. I missed it. Let's cheat right there. And then this side, you remember the pointy vertex story, right? I missed that too, so I'm gonna cheat. How about that? It looks like a parabola, huh? Okay, and then, yeah, why wouldn't it be a parabola? Because yesterday's example, when we differentiated the cubic function, we did get parabola. You know what I'm saying? And then, of course, you notice by now, this is your answer right here, which I generated by computer, and it's exact. You get it? Okay, so I'm going to erase this now. Erase this now, I said. Okay. And then you can have it here. Okay? Okay, that's the feeling it. You had a bunch of these on the homework too, right? Okay, now, and well, we are supposed to find f prime of 2 of this function. Number 1 by finding the derivative. Let's do that, shall we? That was weird. Okay. So let's find the derivative of this. We have done this a few hundred times by now. F prime of x is limit of h approaching 0 of f of x plus h minus f of x over h, like that, eh? Now, then limit of h approaching 0 of, is it 1 over x plus h, our function? Minus 1 over x over h. And whenever you have fraction, what's our tactic here? Feel free to use your microphone.
Break the fraction into 2 different pieces?
No, actually, you want to combine it. Common denominator. Okay, and then 1 over h, right? So we want to that thing multiplying the reciprocal right there, and then x's cancel. I'm gonna take my time. You can cut this corner and then jump to the next line, but I want to show you the most common mistake is right here. -1, you get it? That's the most common mistake. And then if you take the limit, and that gives you -1 over x squared. And for our future purpose, that is, we are getting to the power law, right? So that. How about that? Good? So, therefore, now we can say f prime of 2, of course, is -1 over 4a. Yes. Okay. Now, that was A. This is part A. Now part B. I'm going to do part B in blue. We are supposed to approximate it by using the size of delta x. Okay? So let's do that. F prime of 2 is approximately equal to, remember that? Because if you lose 1 point, that's a big penalty now. So we are supposed to do, and we are supposed to go both ways, so 2.001 minus 1.9998. And then f of 2.001 minus f of 1.999. Okay, can somebody please punch the calculator fast enough to do this? Yeah, right. Who am I kidding, right? Okay. I got this. Okay, children, take out your calculators. Did I show you this before? Amazing, isn't it? You know, I sometimes amaze myself. Okay, let's place it right there. You can see the screen on this thing, right? Okay, did not want you to see all that. Okay, one of the best way to evaluate this thing, because even with a calculator, plugging in this function 1 over, like, ew, right? It's not that easy, all that parenthesis fraction. Although if you know how to use fractions, that's so much better. But this is the best way. Do it with me. So go to y is equal to and enter that as your y. That's our f of x now, isn't it? 1 over x. So enter that, and don't graph it, quit. And this is the shortcut for the fraction. I'm going to give you a minute. Okay, it's been half a minute, but I'm pretty sure you're there. Alpha key, and y is equal to. Oh, there's your fraction. You get it? Enter. And then here is the key, another one. I want to enter this function notation exactly the way you see it. So how do we do that? Alpha again. Alpha is very handy key. And then trace. Then, there's your y1. Bang. You know what I'm saying? Then open parenthesis 2.001 close parenthesis. Minus, not negative sign, minus, and then we do y1 again, alpha trace, that's where y1 is, open parenthesis, 1.999 close parenthesis. You with me so far? Scroll down. I think we can calculate this in our head, right? 0.002. Y'all know you can calculate this in your head without using a calculator, or just type that in now for all it cares. It doesn't matter, right? Okay, ready? That sure looks like this -1 volts now, doesn't it, right? However, how do we present our answer matters a lot here, right? So, see, it's not exactly equal to that right here, right? This is known as, this is true value, but this is a limitation on the calculator. This is known as round-off error. For those of you who will be majoring in computer science, this is a big deal, okay, in computers. Okay, but the way we present it is, now, how many digits are we supposed to present? 6. This is still, okay, not good. This is still approximately -0.250000. Why is it approximately? Why is it approximately right there? This one.
Because it's not exactly equal to it.
Because it's not exactly real using going off of this, right? There's no way you don't know whether this is, although this happens to be same answer, but it's not exactly equal to this expression. You're saying? You get it? This is the rounding. Whenever you round anything, it has to be approximately equal to, it's a big penalty. You get it? Any question about this? Now, did you know that this machine can calculate the derivative for you? Really? Yeah, let's learn how to do that. Math button, math. And then scroll down, 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 down. One more, there. And does that look like derivative to you? Yeah, numerical derivative, okay? And once you press enter, this will be very apparent. Oh, what goes here? There, of course, x, our usual x, right? Because that's how we write it in calculus. And this is our function. Either you can do 1 over x, or if it's a complicated function and we already graphed it before, then you can even do it this way. I'm going to delete this and show you. You can do y1. Both gives you exactly the same answer. And then here, at x is equal to 2. You get it? That's the 2 right there. Let's press enter. Whoa, it's exactly the same thing now, isn't it? That tells you how these programmers at Texas Instrument programmed this thing, this function, numerical derivative. Huh? They did it exactly this way. You get it? So instead of doing all that, if it's tiny delta x, the numerical derivative will simulate, and it's not exact as you can see, it's a round of error compared to our real answer. You get it? Okay, so there's that. Moving down. We have to show that this function is not differentiable. Let's go get that function here. This was, I think I can change it to, it's cubed. And this was 4x, I believe, right? Looks like that. And our thingy is right there, right? Okay, and so our point is, well, this thing actually continues, so it doesn't matter, right? But graphically, let me show you what's going on. If I try to draw a tangent line, and then let this point, this is a left derivative approach, then it's going to be flat. So it's derivative right there. Slope right there is 0. You get it? You see it? However, as soon as I go to the other side, then of course it gives me 4. How about that? With me? Okay. So left derivative we expect it to be 0, right derivative will be 4. So our derivative will not exist. How about that idea? Okay, let's do this by hand now. So I'm going to do f prime of x. Oh, let's do left first. Left derivative. F prime of 0. Something's wrong with this. Is limit of h approaching 0 slightly from the left of f of 0 plus h minus f of 0a over h. Now that is h approaching 0, and then this is h cubed, 0 plus h cubed minus 0 cube a over h. Still with me? And then, of course, h is cancelled, so that gives me limit of h approaching 0 from the left-hand side of h squared, which will give me 0. As we expected, it's flat on the left-hand side of that graph. Okay, I'm going to do the right derivative now. So f prime of 0 is equal to limit of h approaching 0 from the right-hand side of f of 0 plus h minus f of 0 once again over h. Now that is limit of h approaching 0 of 0 plus h, and what's the right-hand side function? It's this one, right? So we have multiply by 4 and minus. In this case, it doesn't matter, but technically we are supposed to use this one right there. You get it? That's where the equal sign is. And from the homework example and the next problem, it'll make a big difference over h. With me? And do you see that this is limit of h approaching 0 of 4h over h, which gives you 4. Right? Left and right derivative don't agree with each other. So what's our conclusion? F prime of 0 does not exist. You get it? Because derivative is defined by this limit of difference quotient, and the limit must exist if and only if two left and the right limit agree with each other, and they don't. We have conflicting answers. So you see why I do not like pointy graphs. If the graph is pointy, then this happens. You get it? So it's a big deal, the pointiness. Other than unnecessary painful memories from the past. But on top of that, this is not good. Okay? Now, so that's the pointiness part. Do we remember what this thing looks like? Okay, let me trigger your memory here. This thingy, what does that look like? It's either x or negative x, right? If x is positive and if x is negative. I'm not going to put equal sign because I'm about to do this. Right, so that function g is almost, oh, whoa, I made a mistake. Of course, I was trying to see if you're paying any attention, and none of you are. Oh, Matthew.
Yes, I was just going to, you wanted to define a function, yes? The absolute value of x over x is one plus line at null of equals 1, and another one at null y negative 1.
Yes, exactly.
And the one at y equals 1 is when x is positive, and y equals negative 1 when x is negative.
Yes. Okay, so let me show you what this graphically. It's not exactly the same as E at the moment, but at the whatever I figured out, it's like this. Right? And then it's undefined that when x is equal to 0. However, now they are forcing you to choose a side. You get it? So since it's undefined, they will define it for you. When x is equal to 0, it is equal to 1. So they want you to fill this circle and leave the other one open. You know what I'm saying? Let's rewrite this function then. Okay, so that g of x can be written this way. G of x could be written as 1 if x is greater than or equal to 0, and negative 1 if x is less than 0. How about that? Do you agree that they are the same thing? Yes. Now, having said that, we are going to find the left and the right derivative. Okay, but can you think conceptually? Right derivative will be 0 because this is 0 right here, right? So let's do that first. It's easier on the right-hand side. So let's do right derivative first this time. So right. So g prime of 0 is, oh, by the way, derivative exists everywhere else. It's just that 0 we might have a problem, right? Discontinuity will cause a problem, as you've seen from homework. 0 plus h minus g of 0 over h as h approaches 0 from the right-hand side, right? Okay, so h approaching 0, 0 plus h, so this term is slightly positive. So we are supposed to use this piece, a 1 minus, and g of 0 is defined to be 1 here, right? There. So it's minus 1 again over h. Okay, so that's 0 over h, isn't it? Let me push this thing down a little bit so I can have a little more room. That is 0 over h. And then earlier period, there was a confusion about this. Isn't that just 0 over 0? Okay, you have to be careful. When we say limit, it means it's approaching 0 but not equal to, right? So this denominator is very close to 0, but it's not equal to 0, and numerator is exactly equal to 0, right? And 0 wins, so this is the 0. You get it? So far, so good? Okay, let's do the right-hand side. Right-hand side, if we try to do it, we are trying to have this point, and if I connect it, it's going to look like this. And I'm pushing this point towards that where this hole is. You get it? So this line will stand up, and do you see that our slope will be infinity? That's what we expect here. Okay, let's see if it gives us that. So left-hand side, g of 0 is equal to limit of h approaching 0 slightly from the negative side, g of 0 plus h minus g of 0 over h. And that is limit h approaching 0. Now, since h is slightly negative, we are supposed to use this piece now, right? So we have negative 1 minus, okay. Now, what is g of 0? That's 1, right? We're supposed to use that piece when it's equal sign belongs right there. So this is 1. You with me? Over h. So that is limit of h approaching 0 of negative 2 over h. So some negative number, problem. Isn't that negative infinity? Negative number over 0? But we want positive infinity looking at this thingy. Can somebody point out why that should be positive infinity instead of negative infinity now? Tricky mathematics.
Approaching 0 from the negative side.
Aha, very good. This is slightly negative number. So we have negative number over very tiny negative number. So it becomes positive infinity, very big number. Not equal to, but very big. You get it? Amazing, isn't it?
Mr. Jim?
Yes.
Wait, shouldn't you technically supposed to put like for the left hand side the second line and the third line, shouldn't you supposed to put like 0 and put the negative on the top for the left? Or do you just ignore the plus and minus sign?
Which one? This one?
No, the limit the h approaches 0. Do you just not put?
Of course. I was trying to see if you're paying attention.
Oh, and the plus on the.
This one plus sign, right?
Yeah.
Weird thing is, I always forget these kind of things all the time, but I never forget to deduct a point if you forget on the test. You see how that works?
Yeah.
I don't know, this brain is so forgetful, but not when I grade. I never miss anything.
Okay.
I know. See, aren't you glad that I never miss anything? Okay. Now, so let's summarize it. When is the derivative? When does the derivative fail to exist? Okay, number one, pointy stuff, right? Pointy is bad. I think I'm gonna use, if I use red, it's more violent, right? Pointy is bad. Because triggers unnecessary painful memories from the past. But also the left derivative and right derivative is different. See, do you know what this function is? F of x is, this one is of course absolute value x, which means the right hand side y is equal to x and left hand side is y is equal to negative x. So do you see the derivative here? F prime here on this side is 1 and F prime here on that side is negative 1. So if we do difference quotient, it'll give us two different answers, 1 and negative 1, wouldn't it? And derivative will fail to exist. Cusp. I still don't know what cusp means. Can you guys taking AP English Lit or Lang tell me what cusp is? Okay, not only is pointy, but it's like reaching vertical, right? That's double bad. Matthew, tell me what cusp is.
I know that cusp means edge.
Edge, it means edge. So how is it different than corner? I think whatever. Yeah.
I don't know. It's more blade-like or something.
Oh, okay. So it's sharper. It's pointier. So this is double whammy. Oh, yeah. Okay. Totally got it. Okay. This function, let's call it g of x. Do you know what this function is? It happens to be square root of x absolute value. Okay, you can decimal it later if you want to, but this is what you get. And this is very sharp and pointy. So right-hand side will be something positive, maybe positive infinity. Left-hand side will be something negative, maybe negative infinity. In any way, this thing fails to have derivative at that point. You get it? Now, well, having said that, move down. Vertical tangent, oh, by the way, for your information, this function happens to be x to the 1/3 power, also known as cube root of x. Now, if I draw the tangent right there, you see that's vertical, right? So what's wrong with it? Well, what's the slope of a vertical line? Undefined, you get it? Undefined. Infinity is disqualified, it's not a number, you get it? So that's where it fails. And then we see in this problem, right? This is like g from above, right? And then jump. So any kind of discontinuity is a problem. And then vertical tangent, and of course, painful memories from the past. None of them are good. Other than that, everything is differentiable. Wait, there's a big word, differentiable. What does that mean? When we say differentiate, that's a verb form of to take a derivative. Mathematicians love to create multiple vocab for exact same meaning. Right, it's one of those. So differentiable meaning, you can differentiate, meaning derivative exists at that point. How about that? Now, having said that, here's a big theorem. If f has a derivative, meaning f is differentiable, then f is continuous. See, so far, every time we have a discontinuity, we had a problem, right? But can we assume that, or, right? Okay. Now, do you know that in logic, converse is not necessarily true, right? If you have if-then statement going this way, the other ways may or may not be true. For example, if I say, idiots will never get an A in this class, some of you might say, oh, what are you saying? Remember, converse is not necessarily true. So what are you saying to me? You're implying something? Okay. So when we prove if-then statement, what is given and what are we trying to prove? Let me just get that out first. Given is the condition, right? That's given. But that is wordy. And you know that I dislike sentences, English sentences, right? Is that nice and concise? That's what it means, right? And we're trying to prove this thing then. After then, we prove this part, right? That's also wordy. Can somebody summarize that using the definition of derivative? Definition of continuity? It has a limit in it. What's the definition of continuity?
Limit of x approaches a of f of x equals to f of a.
Exactly, right? That was the definition of continuity. On the test before, right? You remember failing it? Okay. Now, that's what we are trying to prove, okay? Let's prove it and call it a day. Here's a proof. Now, if I can prove this statement, watch this. And somehow, miraculously, we don't know whether this is true or not yet, but that turns out to be 0. Let's just follow the logic. Have I proven this statement right here? Because when we say limit, it's a limit of this minus limit of that, but limit of constant is still f of a, right? So if the difference of the two is 0, then they are equal to each other, you get it? But We cannot do equal, dot, dot, dot from both sides check. You know, I hate that, right? I'm taking points for that. So no, God, no. So I'm going to start from the left-hand side and I'm going to get to 0. How about that? So that's limit of x approaching a of, let me write it like this. Times x minus a. Is it exactly the same statement as before? Because do these things cancel and give you this back? You have to be careful. You have to be careful. This is not equal to previous line if x is equal to a. Oh, we have to, but. Remember when we say limit, it means x is not equal to a? That's a key concept here, limit, right? If you don't get that right, it'll be forever confusing for the rest of the semester at least. So x is not equal to a, so these two cancel, so they are equivalent. You know what I'm saying? Okay, then it's limit of the first term, which you should recognize by now, and somebody shout out what this expression is, times limit of the second term, right? Property of the limit. Okay, tell me what this first term is.
Is it the alternate definition of
yeah, a prime of it, the derivative, isn't it? Alternate definition. Wow, didn't I tell you that's a big deal, right? Alternative definition of derivative. And second, somebody else tell me what that second limit is then. It's an easy one, you plug it in. Useless kids, 0. Wait a minute, something times 0, is it 0? Is something times 0? Oh, wait, this is a trick question. You have to think about it a little bit. So something times 0, is it 0?
Yes.
Okay, remember when we say limit means it's not equal to this either. It's very close to 0, but not quite equal to, it's approaching 0. So if this thing is infinity, then it may not be 0. Because 0 times infinity, this thing approaching infinity, this thing approaching 0, that could turn out to be anything. That's a chapter 8 concept. So do we have any assurance? I know, complicated now, isn't it? Do you have any assurance that this is not equal to 0? Where do we have it? We need that assurance before we can conclude this is equal to 0. Right there. You get it? It exists, meaning it's not infinity, because infinity is disqualified. You get it? So this is equal to 0 indeed. Mathematicians tend to put this little box color for like end of the proof. Okay. Intermediate value theorem. Quickly, do you know what intermediate value theorem was before even we get to the derivative? Say this is A and this is f of A, and this is B and this is f of B. And then in this case, f of A is less than f of B. Oh, I'm going to put something in here. Okay, and this is continuous function. So let's say this function looks like that. Okay, and now we're going to have a value that is, we'll call it D. D is between f of A and f of B. So let's say that's D right there. You get it? This thing always exists. And then there has to be a C, right? So if this is the case, and f is continuous in point interval A and B, then, if then, remember that arrow, if then there is, this means there exists a C within, let's say, I'm going to write it like that, such that A, C, B possibly equal to where and also f of c is equal to d. What it means is it just assumes every possible, I'm going to throw it. This f of x will assume every possible value between here and here. You get it? So whenever there is a point here, then there's a corresponding value. That's intermediate value theorem. Yes, Ashley.
Class was supposed to end 5 minutes ago.
Oh my God. I'm so sorry. You guys who have a class to get to, you can go. And then I'm almost done. Oh, I got carried away. And for derivative, all we have to do is just put primes. You know what I'm saying? So exact same thing applies to the derivative. Okay, let's call it a day.